Have you ever wondered what lies beyond the planets of our solar system? How far can we explore the vastness of space? What mysteries await us in the interstellar medium? These are some of the questions that motivated the Voyager 1 and 2 missions, two twin spacecraft that were launched in 1977 and are still operating today, more than 46 years later. To date, the twins are the most successful and the longest-running missions in the history of space exploration. They have traveled farther than any other spacecraft, and they have visited more worlds than any other mission. They have made countless discoveries that have changed our view of the solar system and the cosmos, and they have inspired generations of scientists. But their unimaginable journey hasn't stopped yet. Those little mechanical masterminds have been cutting a path through space for nearly half a century, and they're still going strong. They might even get to another star system one day, a few tens of thousands of years from now. Join us as we dig deep into the most amazing scientific discoveries that these spacecraft have made and how they have transformed our understanding of the cosmos. The solar system is a vast expanse of space that consists of the sun, planets, moons, asteroids, comets, and other celestial bodies. It is a collection of objects that revolve around the sun due to its gravitational pull. The sun, being the central and most massive component, provides light, heat, and energy to the entire solar system. The main components of the solar system are the Sun, 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, 5 officially recognized dwarf planets, Pluto, Eris, Haumea, Makemake, and Ceres, numerous moons, thousands of asteroids, countless comets, and various other small bodies. The formation of the solar system began approximately 4.6 billion years ago. It is believed that the solar system evolved from a vast cloud of gas and dust called the solar nebula. As the nebula collapsed under its own gravitational force, it formed a rotating disk that eventually gave birth to the sun and the planets. The process of planetary formation involved the accretion of smaller particles, known as planetesimals, which collided and merged over time, gradually forming larger bodies. Eventually, these bodies became the planets and other celestial objects that make up our solar system today. The solar system is an enormous place, spanning a distance of approximately 5.9 billion miles from the Sun to the outermost regions of the Oort cloud. The Sun, with a diameter of about 864,000 miles, accounts for over 99% of the total mass of the solar system. The planets vary greatly in size, with the largest planet, Jupiter, being more than 11 times the diameter of Earth. To grasp the vast size and scale of the solar system, consider this. If the Sun were the size of a basketball, then the Earth would be the size of a peppercorn located 26 meters away, and Pluto, the farthest recognized object, would be the size of a pinhead located 2 kilometers away. The exploration of the solar system began with early space missions in the mid-20th century. The Soviet Union's Luna program successfully sent robotic missions to the moon, paving the way for future crewed missions. The United States, through its Gemini and Apollo programs, achieved the first human landing on the moon in 1969, a milestone in human space exploration. The space age, which started in 1957 with the launch of the Soviet satellite Sputnik, saw significant advancements in space exploration technology. It allowed for the exploration of planets, moons, asteroids, and comets through both robotic and crewed missions. The study of the solar system expanded rapidly during this era, providing valuable insights into the nature and formation of celestial bodies. But the landmark mission contributed to our understanding and exploration of the solar system is the Voyagers. The Voyager 1 and 2 spacecraft were designed to take advantage of a rare alignment of the 4 giant planets of our solar system: Jupiter, Saturn, Uranus, and Neptune. This alignment occurs only once every 175 years, and it allows a spacecraft to use the gravity of each planet to boost its speed and change its trajectory, enabling it to visit all 4 planets in a single mission. This is known as the Grand Tour. and it was a unique opportunity to explore the outer solar system in detail. The duo were launched in 1977, 2 weeks apart from each other. Voyager 2 was actually launched first, on August 20th, followed by Voyager 1 on September 5th. The reason for this was that Voyager 1 had a faster and shorter trajectory, and it would reach Jupiter and Saturn before Voyager 2. This way, Voyager 1 could test the instruments and the communication system and send back valuable data that could help Voyager 2 adjust its course and optimize its observations. The first destination of the Voyager spacecraft was Jupiter, the largest and most massive planet in our solar system. Voyager 1 arrived at Jupiter in March 1979, followed by Voyager 2 in July. The spacecraft took thousands of images and measurements of the planet and its moons, revealing many surprising features. For example, they discovered that Jupiter has a powerful magnetic field and a complex system of rings, composed of dust and debris from its moons. They also found that Jupiter's atmosphere is turbulent and stormy, with winds reaching up to 600 km/h, and a giant red spot that is actually a persistent hurricane larger than Earth. But perhaps the most astonishing discovery was that one of Jupiter's moons, Io, has active volcanoes that spew sulfur and other materials into space. Io is the most volcanically active body in the solar system, and its eruptions are caused by the intense gravitational pull of Jupiter and its other moons, which deform and heat up Io's interior. The Voyager spacecraft captured stunning images of Io's volcanoes, some of which were erupting at the time of the flyby. The next stop of the Voyager spacecraft was Saturn, the second largest and the most beautiful planet in our solar system. Voyager 1 reached Saturn in November 1980, followed by Voyager 2 in August 1981. The spacecraft took spectacular images and measurements of the planet and its rings, which are composed of billions of ice and rock particles of different sizes and shapes, ranging from dust grains to boulders. The rings are divided into several sections by gaps and resonances with Saturn's moons, and they exhibit complex structures and patterns such as waves, braids, spokes, and arcs. The Voyager spacecraft also discovered several new moons of Saturn, bringing the total number to 22 at the time. One of the most intriguing moons was Titan, the largest and the only one with a thick atmosphere. The atmosphere of Titan is mostly nitrogen, with traces of methane and other organic compounds. The Voyager spacecraft could not see through the dense clouds of Titan, but they detected that the moon has a surface pressure of about 1.5 times that of Earth, and a surface temperature of about 180 degrees. They also found that Titan has a weak magnetic field and a possible subsurface ocean of water and ammonia. The Voyager 1 spacecraft ended its planetary tour at Saturn, as it was diverted to fly close to Titan and obtain more data. This maneuver caused Voyager 1 to leave the plane of the solar system and head towards interstellar space. The Voyager 2 spacecraft, however, continued its journey to the next two planets, Uranus and Neptune. Uranus is the third largest and the most tilted planet in our solar system. Its axis of rotation is almost parallel to the plane of its orbit, which means that it rotates on its side. This causes extreme seasons on Uranus, with each pole facing the sun for 42 years, followed by 42 years of darkness. Voyager 2 arrived at Uranus in January 1986, and it was the first and only spacecraft to visit this planet. The spacecraft took images and measurements of Uranus and its moons, revealing a bland and featureless planet with a faint ring system and a weak magnetic field that is tilted 60 degrees from its axis of rotation. The spacecraft also discovered 10 new moons of Uranus, bringing the total number to 15 at the time. One of the most interesting moons was Miranda, which has a bizarre and varied terrain with ridges, valleys, cliffs, and craters, suggesting a violent and complex geological history. Neptune is the fourth largest and the most distant planet in our solar system. It is a cold and windy world, with the fastest winds in the solar system, reaching up to 2,100 km/h. Voyager 2 reached Neptune in August 1989, and it was also the first and only spacecraft to visit this planet. The spacecraft took images and measurements of Neptune and its moons, revealing a beautiful blue planet with a dynamic atmosphere and a powerful magnetic field that is tilted 47 degrees from its axis of rotation. The spacecraft also discovered 6 new moons of Neptune, bringing the total number to 8 at the time. The most fascinating moon was Triton, which is the largest and the only one that orbits in the opposite direction of Neptune's rotation. Triton has a thin nitrogen atmosphere and a frozen surface covered with ice, snow, and geysers that spout nitrogen gas and dust. The Voyager 2 spacecraft completed its grand tour of the outer planets at Neptune, and it also left the plane of the solar system and headed towards interstellar space. The Voyager 1 and 2 spacecraft have visited more planets than any other mission in history, and they have made countless discoveries that have revolutionized our knowledge of the solar system and its diversity. After their planetary encounters, the Voyager 1 and 2 spacecraft continued their journey to the edge of the solar system and beyond. Their new mission, called the Voyager Interstellar Mission, is to explore the outermost regions of the Sun's influence and to enter the interstellar medium, the space between the stars. The spacecraft are still communicating with Earth and sending back valuable data, despite being more than 20 billion kilometers away from us. The Sun is the source of light and heat for our solar system, but it also produces a stream of charged particles called the solar wind, which flows outward in all directions. The solar wind creates a bubble around the Sun and the planets, called the heliosphere, which protects us from the interstellar radiation and cosmic rays. The heliosphere has several layers and boundaries, which the Voyager spacecraft have been exploring and crossing. The first boundary is the termination shock, where the solar wind slows down abruptly as it encounters the pressure of the interstellar medium. The Voyager 1 spacecraft crossed the termination shock in December 2004, followed by Voyager 2 in August 2007. The second boundary is the heliopause, where the solar wind stops completely and the interstellar medium begins. The Voyager 1 spacecraft crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. The Voyager 2 spacecraft crossed the heliopause in November 2018, joining its twin in the interstellar realm. The third boundary is the bow shock, where the interstellar medium is compressed and heated by the motion of the heliosphere through the galaxy. However, the Voyager spacecraft have not detected this boundary yet, and some scientists think that it may not exist at all, as the heliosphere may be moving too slowly to create a shockwave. The Voyager spacecraft are now exploring the interstellar medium, which is not empty, but filled with gas, dust, magnetic fields, and cosmic rays. The spacecraft are measuring the properties and variations of these components and comparing them with the conditions inside the heliosphere. The spacecraft are also searching for signs of other stars and their heliospheres, which may be nearby or far away. The Voyager spacecraft are expected to keep operating until the mid-2020s, when their power sources will run out and they will go silent. However, they will continue to travel through the interstellar medium, carrying a message for any potential alien civilization that may encounter them. The message is a golden record attached to each spacecraft, which contains sounds and images of Earth and its life forms, as well as greetings in 55 languages and music from different cultures. The golden record is a time capsule and a testament of our existence and our curiosity as we reach out to the unknown. And scientists expect one day Voyager's golden record could answer the question, are we alone in the universe? Are we alone? This question has plagued humankind since time immemorial. And yet, we still don't have a conclusive answer. Despite our incredible technological advancements, we have never received a credible radio signal from, or even the teeniest trace of, extraterrestrial life beyond Earth. The quest to determine if anyone or anything is out there has gained greater scientific footing in the nearly half-century since the article titled "Seeking an End to Cosmic Loneliness," published in the New York Times in 1977. That article described physicists' attempts to pick up radio messages from aliens' publication. The endeavor, known as the Search for Extraterrestrial Intelligence, or SETI, was still in its early stages, and its proponents were struggling to persuade their peers and Congress that the idea was worth funding. Back then, astronomers had yet to spot a single planet outside our solar system. Now we know the galaxy is teeming with a diversity of worlds. Our planet's oceans were once considered exceptional, whereas evidence today suggests that numerous moons in the outer solar system host subsurface waters. Our notion of the range of environments where life could exist has also expanded thanks to the discovery on Earth of extremophile organisms that can thrive in places far hotter, saltier, acidic, and more radioactive than previously thought possible, including creatures living around undersea hydrothermal vents. We're now getting closer than ever before to learning how common living worlds like ours actually are. New tools, including machine learning and artificial intelligence, could help scientists look past their preconceived notions of what constitutes life. Future instruments will sniff the atmospheres of distant planets and scan samples from our local solar system to see if they contain telltale chemicals in the right proportions for organisms to prosper. As Ravi Kopparapu, a planetary scientist at NASA's Goddard Space Flight Center in Maryland, shared, "I think within our lifetime we will be able to do it. We will be able to know if there is life on other planets." Two of the most iconic insights related to the possibility of technological civilizations existing elsewhere in the universe are the Fermi paradox and the Drake equation, which were formulated by Enrico Fermi and Frank Drake, respectively. The Fermi paradox attempts to address the question, "Where is everybody?" By most accounts, Fermi asked this deceptively simple question in 1950 during lunch with colleagues. The simple question has since spurred scientists to better understand the possible reasons that we haven't heard from any technologically advanced alien civilizations. As Harshini Sunil, an astronomy and physics undergraduate student at the University of Colorado Boulder, said, "The Fermi paradox is interesting because it contradicts the possibility of advanced life in our galaxy. If advanced civilizations have existed before us, then they would have had ample time to develop interstellar travel and would have made it to Earth. If we invented interstellar travel, where would we go first? We have the predictions of places for life, but they are still hundreds or more light years away. Even if we could travel at the speed of light, there is no guarantee that we will know exactly where to look. It's like hunting for needles in a haystack." Thus, after all, for Sunil and many researchers, the possibility of finding advanced life is black or white. There is so much we first need to discover and learn before we can start predicting where and if advanced life exists. While the Fermi paradox asks why we haven't heard from anyone, the Drake equation attempts to spin a more optimistic approach to this conundrum. The Drake equation is an attempt to quantify the total number of technological civilizations that might currently exist in the cosmos. To do this, the equation factors in astronomical, biological, psychological, and technological elements. However, because the exact values for each of the equation's variables are largely unknown, the Drake equation tends to estimate the number of potential technological civilizations at anywhere between 1, that's us, and 1,000,000. So, it could be said that the Drake equation serves both as a reality check and a hopeful mantra for those involved in the search for life elsewhere. As Franny Edmondson, an astrobiology senior undergraduate student in the Department of Aerospace Physics and Space Sciences at the Florida Institute of Technology, says, "Running through its argument gives you a bleak outlook on our galaxy's intelligent population, but the objectiveness of the equation is necessary for research. Not every stray signal we detect will be an ET neighbor shouting between solar systems. Still, I remain hopeful when considering the Drake equation because of our own existence. Even with slim chances, our intelligent civilization exists, so there is the potential for others. But the question remains, are we alone? Well, first and foremost, we all have accepted that while humans have a long history of speculating about distant worlds, for much of that time, actual evidence was in short supply. The first planets around other stars, known as exoplanets, were discovered in the early 1990s, but it took until the launch of NASA's Kepler Space Telescope in 2009 for astronomers to understand how common they were. Kepler carefully monitored hundreds of thousands of stars, looking for tiny dips in their brightness that could indicate planets passing in front of them. The mission helped the number of known exoplanets rise from a mere handful to over 5,500. Kepler was built to help determine the prevalence of Earth, like planets orbiting sun-like stars at the right distance, to have liquid water on their surface, a region often nicknamed the Goldilocks zone. While not a single extraterrestrial world has been a perfect twin of our own so far, researchers can use the sheer quantity of discoveries to make educated guesses as to how many might be out there. The current best estimates suggest that anywhere between 10% and 50% of sun-like stars have planets like ours, leading to numbers that make astronomers' heads swim. If it's 50%, that's bonkers, right? As Jesse Christensen, an astrophysicist at Caltech in Pasadena, California, say, there are billions of sun-like stars in the galaxy, and if half of them have Earth-like planets, there could be billions of habitable rocky planets. And that's really insane! But determining whether these planets actually contain organisms is no easy task. Researchers must capture the faint light from an exoplanet and spread it into its constituent wavelengths, scanning for signatures that indicate the presence and amount of different types of chemicals. While astronomers would like to focus on sun-like stars, doing so is technically challenging. NASA's mighty new James Webb Space Telescope is currently training its 6.5-meter mirror and unparalleled infrared instruments on worlds around stars smaller, cooler, and redder than our Sun, known as M-dwarfs. Such places might be habitable, but at the moment, nobody is really sure. For liquid water to be present on their surfaces, planets around M-dwarfs would need to orbit close to their stars, which tend to be more active than the Sun, sending out violent flares that could strip away atmospheric gases and likely leave the ground a dry husk. James Webb has been investigating TRAPPIST-1, an M-dwarf 40 light-years away, with 7 small rocky worlds, 4 of which are at the right distance to potentially have liquid water. The 2 closest exoplanets have already been shown to be devoid of atmospheres, but scientists are eagerly awaiting the results of James Webb's observations from the next 3. They want to know if even those outside the habitable zone can have atmospheres. There's special interest in looking for other planets around M-dwarf stars, because they are far more prevalent than sun-sized stars. And if scientists find them to hold atmospheres, that increases the habitable real estate of the galaxy 100-fold. Once we've found a planet that looks a lot like Earth, then we'll want to start hunting for chemical clues of life on its surface. James Webb isn't sensitive enough to do that, but future ground-based instruments like the Extremely Large Telescope, Giant Magellan Telescope, and 30-meter telescope, which are expected to begin taking data in the 2030s, could tease out the chemical components of nearby Earth-like worlds. Information from more distant targets will have to wait for NASA's next planned flagship mission, the space-based Habitable Worlds Observatory, expected to launch sometime in the late 2030s or early 2040s. The telescope will use either an external star shade or an instrument called a coronagraph to block the glaring light of a star and home in on dimmer planetary light and its potential molecular fingerprints. Which chemicals in particular astronomers should be looking for remains a matter of debate. Ideally, they want to find what are known as biosignatures, molecules like water, methane, and carbon dioxide present in amounts similar to what we find on Earth. What that means in practice isn't always clear, since our planet has gone through many periods when it contained life, yet the quantities of different chemicals varied wildly. But as a piece of good news, recently, there was much excitement when James Webb spotted dimethyl sulfide, a molecule that on our world is made only by living things, on an exoplanet nearly 9 times Earth's size, located 120 light-years away. The results, which have yet to be confirmed, highlight the trickiness of such methods. If dimethyl sulfide is truly present in the planet's atmosphere, then starlight should also break it down to form ethane, a molecule that has yet to be seen. According to Kopparapu, no single gas is a biosignature. You need to see a combination of them. In 2022, Kopparapu and others in the community published a report emphasizing that any particular finding must be placed in the context of its stellar and planetary environment, since there could be many results that seemingly point to life yet have alternative explanations. This problem, how to definitively differentiate between life and non-life, is a perennial one, whether you're looking at distant planets or even phenomena here on Earth. Researchers may soon receive help from algorithmic techniques that can tease out associations too complex for the human brain to fathom. In recent experiments, Robert Hazen and his colleagues took 134 living and non-living samples, including petroleum, carbon-rich meteorites, ancient fossils, and a wasp that flew into their lab, vaporized them, and spread out their chemical constituents. Roughly 500,000 different attributes were identified within each sample's molecular makeup and run through a machine learning program. After the software was trained on 70% of the specimens, the technique was able to recognize with 90% accuracy which of the remaining samples had a biological origin. The device that is used to spread out the chemical components of the samples is around 7 inches long, small enough to be sent on missions to nearby ocean worlds like Jupiter's Europa or Saturn's Enceladus. NASA's Perseverance rover carried a similar instrument to Mars, so Hazen thinks his team's machine learning algorithm could be adapted to sift through its data and hunt for organisms past or present there. And because it relies on molecular relationships rather than detecting specific organic chemicals like DNA or amino acids, which may not be used in other biospheres, the method could allow scientists to look for life entirely unlike what we have on Earth. Such machine learning applications are also starting to find use in SETI, which has in recent years pivoted toward looking for a broader array of visible evidence for tool using extraterrestrial species than before. According to Sophia Sheikh of the SETI Institute, today most in the field are on the lookout for such technosignatures, defined as some remotely detectable signature of technology that we can characterize with astronomical instrumentation. This could be a radio signal, but other evidence could include things like optical laser pulses, giant space-based engineering projects, atmospheric pollution, or even artificial probes that make their way to our solar system. At the Zwicky Transient Facility near San Diego, California, which continuously searches the entire night sky for brief flashes of light coming from unknown sources, engineers are teaching artificial intelligence how to identify features that would not be expected from natural phenomena. As Ashish Mahabal, an astronomer and data scientist at Caltech, says, it's at that point that we can start asking questions. The answers to such questions could help reveal novel astronomical events, or just maybe, a star surrounded by enormous solar panels that feed an energy-intensive alien society. SETI researchers hope that by using such tools, they can help overcome some of their anthropocentric biases. Most recognize that our expectations of otherworldly beings are constrained by our own experience. For example, the search for signs of massive alien solar panels is often based on this assumption that there's always going to be an exponential need for energy. Because of all the avenues currently being explored, many scientists believe that answers to our questions about extraterrestrial life are not far off. But ultimately, The question of our cosmic loneliness is a philosophical one. For most of humanity's history, we didn't believe ourselves to be alone. We filled the heavens with gods, monsters, and mythic creatures. It is only in the modern age that our species has started to worry about its place in the universe. If we find intelligent, or even microbial, life beyond Earth, how will this affect humanity? Would we come together as one with the discovery that we are, in fact, not alone in the universe? Or would we lose our collective minds? Well, let's look at things objectively. First, finding extraterrestrial life would be comforting, since it would help soothe the concerns raised by the Fermi paradox. On the other hand, we don't think that it should dethrone humanity's place in the universe. We, like the animals and plants all around us, are the product of billions of years of evolution, and that in itself is incredible. And whether or not any other part of it harbors life, the cosmos is our home. We can choose to be lonely or to embrace the beauty and wonder all around us. In other words, if we find extraterrestrial life, we have enriched the story of the universe, not diminished ourselves. So, the hunt for alien life presses on. For now, SETI continues to scan the skies for radio signals. James Webb keeps blowing our minds with jaw-dropping images and data. The Mars rovers keep drilling holes near their landing sites, and future missions continue to be planned to explore the outer solar system for signs of life. And yet still, the question remains, are we alone? Perhaps one day, humanity will finally know the answer to this question. But until that day comes, all we can do is press on with our search. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.